combining concepts from evolutionary computation to machine learning training here on Machine Learning Basics. Check this out. Before we get to the main video, I was recording the intro sequence where I have the title slide and I play background music, and I saw some emergent behavior in there. I thought it was super cool, so I just want to point out, watch this one. He misses the ground, but then he slams into the base of the platform and tries to hold there as long as he can to get the best possible score until the game is done. How cool is that? Emergent behavior. I love seeing that kind of thing. Really cool stuff. All right, now on to the main video. The last couple of videos, we've used automation to speed up and make it more convenient to do training, right? So if we wanted to explore hyperparameter space, we could try a whole bunch of different configurations. Or if we wanted to just do a whole bunch of runs in a row, we could do that. Now we're going to be using that automation to get superior results. So what I'm going to show you is our classic lunar lander problem, right? This was our super difficult one, and the brain I have loaded right now is the 10 million iterations training brain, right? So this was as good as we got with just standard machine learning. You'll notice it crashes sometimes, or sometimes it lands and it's very far away from its target. This was, okay, it's passable, but it's not really that amazing, right? This is still better than most people would be able to do for this game. Remember, this is a very hard game, but it's not mind-blowing, right? Again, we're seeing things crash, and every now and then it lands it, right on the money. Does okay. So then we went to imitation learning, and it took us a few tries to get the imitation learning right, but, sure enough, we did better, I think, with the imitation learning than we did with the really, really long run of training. Now, with this new evolutionary technique I'm about to show you, I will pull up the brain that I've done. So this is 3 evolutions. So you don't need a ton of evolutions. And in this case, I think it was 500,000 iterations per evolution. So for a total of 2 million training steps as opposed to 10 million training steps. And so you'll see this guy crash that one, but on the money, close, landed safe, although that target's actually kind of a tricky target. But you'll notice it lands very, very close there, here. That's pretty good. That's okay. That's excellent. And so this is by far the best brain. And look, it's gotten close in every single one of these this time. So by far the best brain that we've seen to date at this game. And again, this is an extremely hard game. And so I don't know if we'll ever get a player that never crashes, maybe with some additional training. But this evolutionary approach has certainly yielded me by far the best results that I've gotten. So the question is how do we... Oh, hey, look, Unity crashed. All right. Good thing I'm done with that. All right. So the question is how do we do this evolutionary approach? And what is that? Well, so here's my other instance of Unity up and running. So we are currently executing an evolutionary run. So you'll notice that we have this third scene in the scenes folder, and we have 4 game objects up here, right? We have our TensorBoard manager. This is exactly the same as it's been the previous settings. We have our run manager. This is for the initial base run of the evolution, right? So in this case, it starts with the word base run, and then our evolution manager changes the run set name over time. Again, same executable, same TensorBoard config, and then again, this continue from saved and continued from model. This is managed actually by the evolution manager as opposed to manually setting that. Configuration manager, again, set as before. I think, going through here, I have some settings that aren't really optimal for this configuration of hyperparameters. It's good enough for demonstration purposes. I showed you the brain that really, really worked, and so this was just kind of a demo batch run. But you'll see, again, we have the summary frequency, sequence length, time horizon. Those are all set. And then the max steps for the very astute of you just changed from 150,000 to 200,000, because what's going on is the evolution manager is actually increasing that for each evolution so that the timeline continues to get longer. So the evolution manager, this is the new part. So the run set name or root, right, is evolution test. So it's going to be evolution test 1, 2, 3, increment. Max generation. So it's how many generations total is it going to do. This is going to do 5 generations. It's probably overkill, and I'm showing this video at, I think, the 3rd generation mark. Yes, it says so right there. Currently generation 3. And it's enough to get the idea across. You don't need a bajillion generations to improve your training. And then, where's your trainer config and run manager, and then at begin run, what do you do? And then on done, it's just saying that evolution is complete. And so you can see in the console how after it says all runs complete, it starts up a new generation, and then it starts up a new run in that generation. So what's going on? The whole idea is that when you train, we've seen that we wanted to do multiple runs of our training because sometimes the machine learns better than others, right? And we'll end up with a much higher score. And so you'll have 2 runs with the same configuration, and the scores can be really, really divergent. And we've seen cases where, you're doing a long training run and you get like 1,000,000 iterations into it, and then it does something and the performance just tanks and it is never able to recover. And so this whole technique is to try to mitigate that somewhat, right? So what we do is we do multiple shorter runs, right? And so in this case, we're doing 50,000, which is probably really too short. But we do a training run of like 50,000 iterations, and then we run it 5 times, and then we find the one that has the best average score, right? And then we make a copy of that, and then we do the next generation, and we make multiple copies of that best performer, and then we train those. And then of those, we find the best performer, and then we make copies of that, and then we continue to train that on. So basically what's happening is in some cases, it's serendipitously learning good things, and in other cases, the learning is poor, and this is a way to just take the best students, to clone them, and then to continue the training with the best students. So that's the idea here. The metric that I'm using to determine who the best students are in this case is just the highest average score. You could, modify that algorithm if you wanted to weight it, because it might have like a peak at the end of training, and mine right now would largely ignore a peak at the end of training, but maybe you'd want to balance a peak score versus average score or something like that. For me, I just took the blanket average score and said whoever has the highest average score seems to be doing the best, and that becomes the parent of the entire next generation, and then we pick up the training from there. So if we go into the run manager, oh, that's right, the run stats got cleared out because we just started a new generation. So I don't have that to show, but I do have TensorBoard up, so I can show you on TensorBoard. Okay. So you can see here, this is generation 1, and there's very telltale signs of what's going on because there's these conspicuous breaks between generations. So this is generation 1, and so this is called evolutionary base, or evolution base, and we'll all start out low, and then some of them do great, and some of them do really not so great. So this is like, 1.3, and then that one is a 3.6. Right, so this is literally almost 3 times better than that one is right off the gate. So we do 50,000 runs of that, and then we continue from this point, and then we go from there. And you can see how these are all much closer. and then they all went down, which is interesting. And again, I think 50,000 runs is probably too short. I probably should have had it at more like a 250,000 or 500,000 steps per generation, but I wanted to really be able to demonstrate this. So, I just picked the 50,000 since it was a fairly short run. And so what you can see is when the new generation comes, they all start from about this point, and then they move on from there, right? And then these ones, and this is, really valuable here, is, again, the difference between the best and the worst isn't huge, but it is significant. It's not just in the noise here. And so again, what we're doing is we're taking the best student, cloning them 5 times, and then continuing the next run. And then what's happening here is, and again, we have taken the best student and we're going to clone it 5 times and continue the training. So we're going to do this 5 sets of 5. So there's going to be 25 total runs, and after each 5 runs, we pick the best and we continue training from there. And I have absolutely, again, you saw the evidence. The brain that we've had where I ran this did much, much better than any of the other training and algorithms in much less time. So how do you get better performance out of this? We have a variety of means. Probably the best thing to start off with is a higher run number, like 5 or 10 different runs, and then give them a fair amount of time and then let it go overnight, and you just kick it off. 3 generations is probably pretty good. It might be 4. So what happens is, for each generation that you do this, you notice that there's a huge amount of variance in the behaviors here, right? And then in the next generation, that variance condenses a lot. Now, we're never as, there goes another one just started up. We're never as bad as the worst 2, right? So if you just do one run like we're used to doing, especially in the, early days, right? And you just happen to get one of these poor runs, you might never actually ever improve. And so all of these are better likely than either of these. So, doing this helps you just call, which training runs did really well and which didn't. Now, the other thing that's happening is in this evolutionary algorithm that I'm using, I am not resetting the training rate, right? So we start with a one given training rate, and then we are increasing the number of total steps. And so what's happening is, over time, excuse me, over time, the learning rate is evening out, right? So each successive generation starts at proportionally a lower learning rate. So that's another thing that you can play around with a little bit. Certainly knowing that you want a higher learning rate, especially for your early generations, because it has a large effect. And again, this is another reason why it may be good to do a much longer initial training run, and then in the further training runs, you could even play around with each successive generation, maybe make it shorter, or you bump the learning rate back up so that when it starts off again, instead of being halfway through, maybe you double the learning rate so that it starts at a very high learning rate again and does that. So in my case, I haven't been resetting the learning rate, and I've still gotten some very, very strong results. And again, so you can see how this is really converging. There is a concern about finding a local optima, right? Can you get to a place where because you picked one really successful item at the beginning and then are continuing to do your training from that, are you going to find a local optima and really just optimize for that? And that's a valid point and a valid question. And so the way to deal with that is, for a lot of genetic algorithms and whatnot, is to continue to introduce some randomness or some other behaviors. So you can do that by, again, mucking with the learning rate. You can train newcomers, right? So, maybe in this case, I don't really love where any of these ended up. And so you could set things up as like, if my whole generation here is lower than my best average here, which is the case, for this iteration, then maybe you go back to, you go back a step and automate training a whole new initial population and just say restart. If my second generation is worse than my first generation, then maybe I just need to redo from start. And those are the things that we can do fairly simply now, right? It's all in there, easy to access code, and we can just go into Unity and make changes as we need. So this is the kind of thing where it'll probably take some tweaking for your problem, and again, some adjustments to get it to work with your particular data set. But as you can see, certainly with the earlier demo, I've gotten some very, very good results. And again, it helps the whole thing converge on what I think are going to be better values. Again, because if you just get unlucky with one of these two lower ones, you could be spending an entire night of training and you're training the wrong guy. So then after I do some initial training like this, and I get kind of like the best of breed in the beginning, then you can also just go to a more traditional machine learning training where you say, all right, I know I have good initial conditions, and then I'm going to just set that up for another long run, and so that I can tack on another 8 million iterations or something, so that it has the ability to optimize, right? So that you can really, really refine it. And so that's actually not something that I did in the previous demo, right? I did a base and then 3 generations, each of which I think was 500,000 iterations. So the total training time for any one student was 2 million. So I did, 500,000 initial, and then, did my cut, made my copies, and then went from there. And so actually, when I did that, I did it manually. So now that we have it automated, it's super easy to do. So I encourage people to play around with it and give it a shot, because I have had some phenomenal success by being able to, continually take the best of breed and then using that over and over again. And we see like we may have a little bit of a breakout start here, like this red line has picked up and is solidly improving. So hopefully that one won't tank and will continue to improve, because that's the kind of thing that we're looking for. So as always, if you have any questions, thoughts, please feel free to put them in the comments. I am very intrigued to hear what kind of projects people are working on, and also help folks out if they hit any snags along the way. In the meantime, thank you very much for watching. If you found anything here useful, please go ahead and hit the like button, subscribe button, and also I want to give a big shout out to my patrons over on patreon.com who are helping support the show financially. It's thanks to folks like you that I am continuing to make these videos and continuing to build out this video series. I think we're done for automations. We've done 3 videos on automation. I think I've said pretty much everything that I've wanted to say about automation. So we're going to probably be going back into some of the training stuff, multi-brain training. I'm interested in a brain of brains training. I think might be interesting. There's a whole bunch of topics that we haven't covered yet. We are starting to get a little more advanced, so I may start up a new playlist as we get into kind of more intermediate level stuff, as we're kind of completing up what I would consider the basics. And where did we end up with that one training run? Oh, no, same place as the blue one did. Although I will say both of these are showing an improvement over all of the previous generations. So we are seeing slight improvements here as the training kicks in appropriately. So this is doing about what I would expect. It's forcing things to converge, and then once it's converged enough that you're happy with it, again, this is pretty converged. I'm probably fairly happy with this. I wouldn't expect any one of these to tank or be an absolute standout, amazing one after this. So 3 generations, 4 generations, and then you can stop doing the generations and then just set it to be a really long run and optimize and see where you get from there. So looks good. Again, bunch of videos coming up on different topics, probably getting into more machine learning intermediate stuff, because we're getting out of the basics. But I'm also interested, if people really want me to cover more of the basics, I can also cover different scenarios and different examples of some of the real basics of machine learning, so that we could get into shooters or stealth games or something like that. There's a whole bunch of fun things that we could do like that. So comments below, questions below, and thank you very much, and happy learning.